In the silent, unending theatre of the cosmos, there are whispers. They are not sounds, but tremors in the fabric of space-time. They are not stories, but echoes from an age so remote. The light carrying them began its journey when our own Earth was nothing more than a formless cloud of dust and gas. These faint messages speak of monsters, not creatures of myth, but titans of physics, entities so extreme they strain the very limits of our imagination and challenge the foundations of our cosmic theories. We search for them in the deepest wells of the night sky, with instruments designed to capture the ghosts of ancient light. We are looking for the anomalies, the outliers, the things that should not be. And in a quiet patch of sky, in the direction of the hunting dogs, we found the king of all phantoms. It is an object that wears the mask of a distant, unassuming star, a simple pinprick of aquamarine light on old photographic plates. But this disguise conceals a truth of such bewildering scale, it forces us to reconsider everything we thought we knew about the birth and growth of structure in the universe. It is known by a designation from a forgotten catalogue, TON 618. The name is mundane, technical, almost deliberately anonymous, yet it signifies the most massive black hole ever discovered by humanity. It is not merely large, it is an ultramassive behemoth, a gravitational sovereign ruling over an ancient distant galaxy. To call it a monster is an understatement. It is a rupture in reality, a point of infinite density weighing as much as 66 billion of our own suns. This is not a number the human mind can truly grasp. It is an abstraction, a piece of celestial arithmetic that describes an object of impossible proportions. Imagine our own solar system, a vast expanse that takes our fastest probe, Voyager 1, over 3.5 decades to even approach its edge. The event horizon of TON 618, its boundary of no return, is so colossal that it could swallow our entire solar system whole, not just once, but more than 11 times over, side by side. Light itself, the fastest thing in existence, would take weeks to complete a single orbit around this gravitational titan. This is a shadow of such profound dimensions that it redefines the very concept of big. And here lies the central, unnerving mystery. This is not just a story about a record-breaking discovery. It is the story of an object that, according to our best models of the universe, should not, and perhaps cannot, exist. Its presence on the cosmic stage is a profound enigma. It is a question mark written in the language of bent starlight and warped space, and the most brilliant minds on our planet are struggling to formulate an answer. Why can't scientists explain TON 618? The quest to understand this leviathan takes us to the dawn of time, to the very edge of physics, and into the heart of the deepest darkness imaginable. Our journey into the abyss begins with a simple observation. From our vantage point, we do not see the black hole itself. Darkness, by its very nature, cannot be seen. What we witness is the cosmic wreckage of its feeding frenzy. TON 618 is the engine powering a quasar and quasi-stellar radio source. This is the single most luminous type of object in the known universe. Surrounding the black hole is an enormous, swirling vortex of matter, an accretion disk comprised of gas, dust, and shredded stars, all spiraling toward their inevitable doom. As this material is pulled inward by the black hole's immense gravity, it is compressed and heated to unimaginable temperatures, millions of degrees hotter than the core of any star. This inferno of superheated plasma glows with a ferocity that is difficult to put into words. The light generated by this accretion disk is 100 trillion times brighter than our own sun. It shines with the fury of 2,000 galaxies like our Milky Way, all concentrated into a region of space only slightly larger than our solar system. The quasar of TON 618 is a lighthouse in the cosmic dark, so brilliant that it completely outshines the hundreds of billions of stars in its own host galaxy, rendering them all but invisible to our telescopes. It is a bonfire of such epic proportions that we can see it from more than 10 billion light-years away. But this very brilliance, this testament to its voracious appetite, is the first clue in the mystery of its impossible existence. The light we are seeing today left TON 618 when the universe was a mere toddler, just over 3 billion years old. This discovery places a colossal, fully formed giant in the nursery of the cosmos, and this is where our understanding begins to fracture. How does a black hole grow so astonishingly large, so terrifyingly fast? To appreciate the scale of this problem, we must first understand the conventional story of how black holes are born and raised. The process begins with the death of a single, magnificent star. A star at least 20 times more massive than our Sun lives a short, violent life. It burns through its nuclear fuel with reckless abandon. When the fuel runs out, the outward pressure from fusion ceases. Gravity, the relentless architect of the cosmos, finally wins the eons-long battle. The star's core collapses in on itself catastrophically. The implosion is so powerful that it crushes matter out of existence, squeezing it into a point of infinite density, a singularity. The outer layers of the star are blasted away in a supernova explosion, one of the most energetic events in the universe. What remains is a stellar mass black hole, a newborn phantom with a mass perhaps 10 or 20 times that of our Sun. These are the common black holes, the seeds from which greater things might grow. At the heart of most large galaxies, including our own Milky Way, we find supermassive black holes. Our galaxy's central black hole, Sagittarius A star, is a respectable 4 million solar masses. The prevailing theory is that these giants grew over billions of years through two primary mechanisms: steady accretion and violent mergers. They act as cosmic sinks, slowly sipping on a steady stream of interstellar gas and dust. Occasionally, an unlucky star wanders too close and is torn apart in a tidal disruption event, providing a more substantial meal. The second method is far more dramatic. When galaxies collide and merge, as they frequently do, their central black holes are drawn together by gravity. They begin a long, elaborate celestial dance, orbiting each other for millions of years, shedding vast amounts of energy as gravitational waves, ripples in the fabric of space-time itself. Eventually they coalesce, merging into a single, more massive black hole. This is the standard model, a slow, patient process of growth, spanning the vast majority of cosmic history. It is a narrative of gradual accumulation, of countless meals and epic collisions, unfolding over the immense timescale of 13 billion years. TON 618 utterly demolishes this elegant timeline. It is not a product of gradual patient growth over the age of the universe. We are observing it as it was in the distant past, a mere 3 billion years after the Big Bang. The cosmos at that time was far more compact, chaotic and dense. Galaxies were just beginning to form and assemble. The universe simply had not had enough time for a black hole to grow to 66 billion solar masses through these conventional means. It would be like finding a fully grown giant sequoia, hundreds of feet tall and thousands of years old, in a forest that was planted only a decade ago. It makes no sense. The numbers simply do not add up. Even if a seed black hole formed from the very first generation of stars and consumed matter, and merged with other black holes constantly, without pause, from the moment it was born, it could not reach the titanic mass of TON 618 in the available time. This chronological paradox forces scientists to explore more exotic, more radical theories for its origin. Perhaps the seeds of these ultramassive black holes were not small at all. One compelling, though still debated idea, is the theory of direct collapse black holes. In the primordial universe, before stars had widely seeded the cosmos with heavy elements, there existed immense pure clouds of hydrogen and helium. These clouds, hundreds of thousands of times the mass of our Sun, could have become gravitationally unstable. Under specific pristine conditions, instead of fragmenting to form a cluster of normal stars, one of these colossal clouds could have collapsed directly, in its entirety, into a single, massive black hole. This process would bypass the stellar mass stage completely, creating a heavy seed black hole from the outset, weighing in at tens of thousands, or even 100,000 solar masses. This would give a future monster like TON 618 a crucial head start. It would be born not as an infant, but as a young giant, already possessing the gravitational clout to dominate its surroundings. This direct collapse model provides a potential pathway, a possible solution to the timeline problem. However, the conditions required for such an event are exceptionally rare. The gas cloud must be incredibly pure, with almost no heavy elements, and it must be bathed in a specific intensity of ultraviolet radiation from nearby star-forming regions to prevent it from cooling and fragmenting. Finding a location in the early universe that met all these stringent requirements would be like finding the one perfect incubator in a cosmic maternity ward. While plausible, it remains a hypothetical scenario, a ghost of a process we have yet to observe directly. But even if we grant TON 618 a supersized seed, its origin story is only the first chapter of its mystery. The second, equally baffling problem is its rate of growth. It is one thing to be born big, it is another to sustain an appetite that seems to defy a fundamental law of physics. This law is known as the Eddington limit. Imagine a campfire. The fire produces heat and light, which radiates outwards. This outward pressure can be felt. If you try to throw fine sawdust onto the fire, the rising heat and light will push some of the sawdust away, preventing it from all falling in at once. A quasar's accretion disk works on a similar principle, but on a cosmic scale. As matter falls toward the black hole, it heats up and radiates an immense amount of energy. This outward flood of radiation, this light pressure, pushes back against the very gas and dust that is trying to fall in. The Eddington limit is the theoretical maximum rate at which a black hole can accrete matter. It represents a point of equilibrium. If the black hole tries to feed any faster, the radiation from its accretion disk will become so intense that it will literally blow its food away, choking off its own supply. It is a natural feedback loop, a cosmic self-regulation mechanism that should put a speed limit on a black hole's growth. TON 618 appears to be a cosmic scofflaw, flagrantly violating this speed limit. To reach its observed mass by the time we see it, it must have been consuming matter at a rate that is at, or even far beyond, its calculated Eddington limit for a vast period of its existence. It was devouring on average the equivalent of several suns' worth of material every single year. Every year, for hundreds of millions of years. The sheer luminosity of its quasar is a testament to this hyper-aggressive feeding. It is burning through its fuel so ferociously that it seems unsustainable. How is this possible? How can it overcome the very radiation pressure it generates? Scientists are exploring several possibilities, each pushing the boundaries of astrophysics. Perhaps the accretion disk is not the simple, uniform, thin disk we often imagine. It might be clumpy and porous, allowing some matter to fall in through gaps and shadows where the radiation pressure is weaker. This would be like finding protected channels in a fierce wind, allowing some material to sneak through the storm. Another possibility involves what is known as super-Eddington, or hyper-Eddington accretion. Under certain conditions, the disk might become geometrically thick and puffy, forming a kind of funnel or cone structure. In this configuration, much of the radiation might be beamed outwards along the poles, like the jets of a particle accelerator. This would clear an escape route for the intense light, allowing matter to continue flowing in unimpeded along the equatorial plane. The black hole could effectively vent its exhaust in two directions, while continuing to feed from all other sides. These models are complex and rely on sophisticated computer simulations of plasma physics and magnetohydrodynamics under extreme gravity. They offer a potential escape clause from the Eddington limit, but they also paint a picture of a far more chaotic and violent environment than our simpler models had predicted. The very existence of TON 618 suggests that nature has found a way to build these titans, and to do so with shocking efficiency. It tells us that our understanding of accretion physics, the process of how black holes feed, is incomplete. This single object serves as a powerful anchor for our theories, a data point so extreme that any successful model of galaxy formation must be able to account for its creation. If your theory cannot produce a 66 billion solar mass black hole in less than 3 billion years, your theory is wrong, or at least unfinished. This leads us to the third great mystery, the cosmic context. A black hole of this magnitude does not exist in a vacuum. It resides at the heart of a galaxy, and its relationship with its host is a profound and intricate dance of creation and destruction. A quasar like the one powered by TON 618 is not a gentle giant. It is an active, violent engine that profoundly shapes its entire galactic environment. The same intense radiation that makes the quasar so bright also pours out into the host galaxy, heating up gas clouds and potentially disrupting or even halting the process of star formation. Furthermore, the twisting magnetic fields in the accretion disk can act like a colossal cosmic slingshot, launching twin jets of particles away from the black hole at nearly the speed of light. These jets can travel for hundreds of thousands of light years, punching vast, empty cavities into the intergalactic medium. This process, known as feedback, is one of the most important but least understood aspects of galaxy evolution. The central black hole can act as a galactic thermostat. Its energetic outburst can blow away the cold gas necessary for forming new stars, effectively quenching the galaxy and stopping its growth. In the case of TON 618, we are witnessing feedback on an almost unimaginable scale. The energy being pumped into its host galaxy is immense. Is this ultra-massive black hole a builder or a destroyer? Did its powerful gravity help to gather the initial material that formed the galaxy in the first place? Or has its violent, luminous phase sterilized its surroundings, ensuring that its host galaxy will forever be a barren wasteland, its potential for creating new suns and new worlds extinguished? Answering this question is incredibly difficult, precisely because the quasar is so blindingly bright. Trying to study the host galaxy of TON 618 is like trying to study the filament of a light bulb while it is switched on. The glare is simply overwhelming. Astronomers must use clever techniques and observations in different wavelengths of light to try and subtract the quasar's glare and catch a faint glimpse of the starlight from the underlying galaxy. What little we can discern suggests a large, messy, perhaps chaotic galaxy, likely in the midst of multiple mergers, which would help to funnel the enormous quantities of gas required to fuel such a luminous quasar. But the details remain shrouded, hidden behind a curtain of light generated by the very monster we are trying to understand. The story of TON 618 is therefore not just the story of a single object. It is a critical piece of the puzzle of how the first galaxies formed and evolved in the young universe. These ultra-massive black holes may be more than just cosmic curiosities. They may be the primary architects of galactic structure. Their immense gravity could have provided the initial anchors around which the first galaxies coalesced. Their subsequent feedback could have been the deciding factor that determined which galaxies would continue to form stars and which would become red and dead. To understand the universe we see today, we must first understand the role these primordial giants played in shaping it. So where does this leave us? We are confronted by a celestial titan whose very being challenges our models of time, growth, and cosmic influence. We have theories, plausible pathways, and sophisticated simulations. We speak of direct collapse seeds and super Eddington accretion flows. But these are, for now, educated hypotheses, not settled facts. They are the best stories we can craft with the physics we currently possess. The truth is, we cannot definitively explain how TON 618 came to be. It represents a frontier of astrophysics, a known unknown that beckons us forward, and the questions it raises ripple outwards into even more speculative realms. If nature can build a black hole of 66 billion solar masses, is that the limit? Or are there even larger entities lurking in the cosmic dark? Some theoretical models allow for the existence of so-called stupendously large black holes, or slabs. These are hypothetical black holes with masses ranging from 100 billion to quadrillions of solar masses, formed not through standard astrophysical processes, but perhaps from the collapse of vast overdensities in the very early universe. We have no evidence that such objects exist. But the discovery of TON 618, an object once thought to be impossibly large, certainly makes the idea feel less like pure science fiction. It reminds us that the universe has a far greater imagination than we do. And what is the ultimate fate of this cosmic behemoth? The quasar we see is a temporary fleeting phase. In a few 100 million years, perhaps 1 billion, TON 618 will have consumed all the readily available gas in its vicinity. Its brilliant accretion disk will flicker and die. The great cosmic lighthouse will go dark. The host galaxy, long suppressed by the glare, will finally become visible. What will remain is the black hole itself, a silent, invisible abyss of 66 billion solar masses, adrift in the eternal night. For an almost infinite amount of time it will simply exist, a gravitational ghost, its presence felt only by the silent, orderly orbits of the stars in its galaxy. It will be a monument to a more violent, more luminous epoch in cosmic history. Trillions upon trillions of years will pass. The universe will expand, cool, and darken. The last stars will burn out, leaving a cosmos filled with cold embers and degenerate remnants. Even in this cold, dark future, TON 618 will endure, but not forever. According to the theories of Stephen Hawking, black holes are not entirely black. They are predicted to emit a faint, incredibly weak thermal glow known as Hawking radiation. This process is agonizingly, incomprehensibly slow for a black hole of this size. As it radiates, it loses mass, an infinitesimal amount at a time. For TON 618, the timescale for it to evaporate completely is on the order of 10 to the power of 100 years. This is a number so large it is functionally meaningless. It is 1,000 trillion times longer than the current age of the universe. It is a timescale that will see the heat death of the cosmos itself. Eventually, after an eternity of eternities, in the final fading moments of a dying reality, TON 618 will finally disappear in a final faint flash of energy. Its story, written across the entire lifespan of space and time, will finally conclude. We stand here today, at this brief, fleeting moment in cosmic history, able to look back across 10 billion years of time and see this giant in its glorious, violent youth. It is a privilege and a profound challenge. TON 618 is not a failure of science. Its unexplained nature is not a mark against us. On the contrary, it is the engine of scientific progress. It is a signpost, pointing directly at the gaps in our knowledge. It is a beautiful, terrifying, and awe-inspiring declaration that there are still fundamental truths about the universe we have yet to uncover. It forces us to be more creative, to push our theories harder, to build better telescopes, and to ask bolder questions. The inability to explain this object is an invitation to a grander adventure. Somewhere in its impossible mass, its incredible brightness, and its ancient light, lie the clues to a deeper understanding of the cosmos, a new chapter in the story of how everything came to be. The giant in the dark is waiting. It holds its secrets close, challenging us to solve the riddle of its birth, a riddle that is ultimately about our own cosmic origins. And the quest for that answer is, and always will be, why we continue to look up at the stars. What does it sound like when a monster sleeping for centuries begins to stir in the heart of its own kingdom? For us, the question was not a matter of sound, but of light. 26,000 light-years away, in the deepest, most chaotic and star-choked regions of our Milky Way, a faint, insignificant smear of hydrogen gas had embarked on a journey of no return. It was an ephemeral traveller, a ghost of a thing barely visible even to our most powerful infrared eyes, yet its trajectory was as unambiguous as a death sentence. It was falling inexorably towards the one place in our galaxy from which nothing, not even light, has ever escaped. It was falling towards the abyss we call Sagittarius A. To understand the magnitude of this impending collision, you must first cast your mind into the galactic core, a place so violent and so magnificent it defies earthly comparison. This is not the serene pinpricked darkness of our suburban skies. This is a celestial metropolis on fire, a swirling maelstrom of 1,000,000 stars packed into a space so tight that if you lived on a planet, there your night would be perpetually ablaze, a sky with 1,000 suns. Here stellar winds howl at millions of miles per hour, shredding entire solar systems. Colossal blue giants living fast and dying young explode in supernovae that flashboil entire worlds. Pulsars, the hyperdense corpses of dead stars, whip around like gravitational gyroscopes, sweeping the cosmos with lighthouse beams of lethal radiation. This is the crucible of creation and destruction, a cosmic engine roaring with the fury of constant birth and cataclysmic death. and at the very centre of this symphony of chaos there is a point of perfect, terrifying silence. A gravitational titan holding this entire galactic storm in its thrall. It has a name born of astronomical convention, Sagittarius A, but a name does little to capture its essence. It is our galaxy's supermassive black hole, 4 million times the mass of our Sun crushed by its own gravity into a singularity, a point of infinite density. It is the ultimate anchor, the hub around which every star, every nebula, every planet and every one of us completes a slow, majestic 200 million year orbit. For all its power, however, Sagittarius A is a quiet monster. Compared to the ravenous quasars we see blazing in the hearts of younger, more distant galaxies, ours is practically dormant. It sits in the dark, fasting. Its last significant meal was likely millions of years ago, and the evidence of that feast is long gone, swallowed into the silent eternity behind its event horizon. We can only infer its presence from the frantic, impossible orbits of the stars closest to it, stars that whip around this invisible point at breathtaking speeds, some completing their circuits in just a handful of years, moving at a fraction of the speed of light. They are the frantic dancers to a song only gravity can play their motion, the only visible proof of the phantom in their midst. For astronomers, this placid giant has been a source of profound frustration and unending fascination. We had the theories, the elegant mathematics of Einstein, that predicted the behaviour of space-time in its presence. We had the models that told us how a black hole should feed, how it should tear matter apart and ignite it into a blaze of high-energy radiation before consumption. But we had never seen it happen. Not up close, not in our own cosmic backyard. Our monster was asleep, and we had no way to wake it. Until the year 2011. That was when astronomers painstakingly tracking the orbits of those central stars noticed something new. It was a small elongated blob of gas which they designated G2. It wasn't a star. It was far too cool, too diffuse, too fragile. It was a lonely cloud, perhaps 3 times the mass of the Earth, drifting through the most dangerous neighbourhood in the galaxy. And when they calculated its path, a breathtaking realisation rippled through the global scientific community. G2 was not in a stable orbit. It was on a kamikaze dive, a hyperbolic trajectory that would take it skimming perilously close to the black hole's edge. Its closest approach, its periastron, was predicted for 2013. The universe, it seemed, was about to serve our sleeping monster a meal right on cue, right before our waiting eyes. Suddenly we had a front-row seat to the most exclusive dinner party in the cosmos. The excitement was electric, a once-in-a-generation opportunity that transcended scientific disciplines. This wasn't just about watching something get destroyed, it was about using that destruction as a lantern in the dark. G2 was a cosmic probe sent by chance into a region we could never hope to visit. The questions this single fragile cloud promised to answer were among the most fundamental in astrophysics. First, and most simply, what happens when a black hole feeds? We believe that as matter falls in, it doesn't just drop straight down. Instead, tidal forces, the same forces that cause our ocean tides, but magnified to an unimaginable degree, should stretch the cloud. This cosmic spaghetti-making, or spaghettification, would pull the front of the cloud faster than the back, elongating it into a streamer of incandescent gas. This streamer, we predicted, would then be captured by the black hole's gravity, not immediately falling in, but whipping around it. It would form a temporary miniature accretion disk. Imagine a celestial buzzsaw of superheated plasma, a swirling vortex where friction and magnetic fields would heat the gas to millions of degrees, causing it to glow brilliantly in X-rays before finally taking the final plunge. For the first time we would witness the flicker of the furnace. We would see Sagittarius A light up, awakened from its long slumber by this morsel of gas. The brightness of that flare, its duration, its spectrum of light, all of it would provide a direct measurement of the physics of accretion, the process that powers the most luminous objects in the universe and built the very galaxies themselves. But the promise ran even deeper, touching the very fabric of space-time. According to Albert Einstein's theory of general relativity, the immense gravity of Sagittarius A doesn't just pull on things, it fundamentally warps the geometry of space and time around it. Light itself, the fastest thing in the universe, must follow these warped contours. As G2 was torn apart and began to glow, the light from that dying gas would have to travel to us through this gravitational labyrinth. We expected to see its path bent and twisted. We anticipated observing a phenomenon known as gravitational redshifting, where light climbing out of the black hole's deep gravity well would lose energy. Its wavelength stretched towards the red end of the spectrum, as if it were getting tired from the climb. Watching the exact nature of this distortion measuring precisely how much the light was stretched would be one of the most stringent tests of Einstein's theory ever conceived. It was a chance to verify his century-old predictions in an environment of extreme gravity, a laboratory forged by nature that we could never hope to replicate on Earth. This was not just about a black hole, it was about the fundamental rules that govern reality itself. And then there was the ultimate prize, a glimpse of the edge, the event horizon. The point of no return is by its very definition invisible. It is a one-way door in space-time, a theoretical boundary beyond which the universe as we know it simply ends. We can never see what lies behind it, but by watching G2's material swirl and accelerate by pinpointing the exact moment its light winked out as it crossed that threshold, we could map the shape of that invisible shore. We could watch matter perform its final frantic dance before disappearing from our universe forever. It was the closest we could ever come to probing the abyss itself. This single, unassuming gas cloud was poised to illuminate the nature of accretion test, the limits of relativity, and define the boundary of the most mysterious objects in existence. The cosmic gift was almost too good to be true, so we prepared. A global campaign of observation began, unprecedented in its scale and singular focus. On the high dry deserts of Chile, the European Southern Observatory's Very Large Telescope, an array of 4 colossal 8-meter instruments fixed its gaze on the galactic heart. On the summit of Mauna Kea in Hawaii, the twin Keck telescopes, the largest optical instruments in the world, did the same. Radio telescopes from the Very Large Array in New Mexico to the Atacama Large Millimeter Array listened for the faint radio hums that might signal the cloud's disruption. High above the distorting haze of Earth's atmosphere, space-based observatories like the Chandra X-ray telescope and Swift Gamma-ray burst mission were put on high alert, waiting for the high-energy fireworks that models all but guaranteed. Years were spent collecting baseline data measuring the faint quiescent glow of Sagittarius A in its slumbering state, so that any new activity, no matter how subtle, would be instantly detected. Astronomers ran thousands of computer simulations, each one a slightly different prediction of the coming spectacle. Some models showed a brilliant dramatic flare-up. Others predicted a more gradual simmering event. Debates raged at conferences and in academic halls about the exact nature of the cloud, its origin, and the precise sequence of its demise. But on one thing nearly all agreed something was going to happen. The laws of physics demanded it. A fragile cloud of gas cannot dance with a 4 million solar mass black hole and emerge unscathed. The anticipation in the astronomical world was a palpable force, a slow burn tension that built month by month, year by year, as G2 continued its inexorable plunge. For nearly 2 years, the world's greatest telescope stared unblinking at a single point of darkness in the sky, waiting for a ghost to be eaten by a monster. As 2013 arrived and G2 rounded the point of closest approach, the tension reached its zenith. The cloud was now deep within the black hole's gravitational domain. Data poured in from around the world, frantically processed and analysed. Every astronomer held their breath, waiting for the first sign of the predicted flare, the burst of X-rays that would announce the feast had finally begun. They waited, and they watched. The weeks turned into months. The expected fireworks display the brilliant death cry of a gas cloud shredded by a titan never came. The great cosmic meal we had all gathered to witness was bafflingly a non-event. Sagittarius A remained quiet, its hunger seemingly unabated. The cloud G2 appeared to have survived its perilous journey, emerging from the other side, stretched and distorted but remarkably frustratingly intact. The monster had not eaten. The silence from the galactic centre was more profound and more puzzling than any explosion could have been. It was a result that defied our most confident predictions, sending shockwaves of confusion and exhilarating new questions throughout the scientific community. The universe, it seemed, was not interested in following our script. The simple dramatic story of a lone gas cloud meeting its doom was instantly obsolete, replaced by a far deeper and more complex mystery. Our failure to predict the outcome was not an ending, but a radical new beginning. It forced us to ask a startling question. If this traveller wasn't just a simple cloud of gas, what in the cosmos was it? And why, when faced with the most powerful gravitational force in the Milky Way, did it refuse to be devoured? It began not with a bang, but with an enigma. A profound and unnerving silence from the very heart of our own galaxy. For centuries we had gazed toward the constellation Sagittarius, toward the densest, most brilliant river of stars in our night sky, and assumed that the core of the Milky Way would be a place of unimaginable radiance. A celestial throne room blazing with the light of 1 billion suns packed into a space smaller than our minds could comfortably fathom. Yet when our first radio telescopes listened in during the 1930s, what they heard was not a triumphant fanfare, but a persistent, inexplicable hiss. A whisper of static from the galactic centre, a ghost in the machine. This was the first breadcrumb, the first hint that the centre of our cosmic home was not what we expected. It was something other, something missing. The problem we soon realised was one of sight. A great smoky curtain of interstellar dust, trillions of miles thick, hangs between Earth and the galactic core, absorbing and scattering visible light like an impenetrable fog. To our eyes, the heart of the Milky Way has forever veiled its secrets, locked away behind a shroud of gas and microscopic grit. For decades, that cosmic whisper was all we had, a tantalizing clue from a crime scene we could not see. The source of the hiss was eventually pinpointed with greater and greater accuracy. A compact, ferociously energetic object designated Sagittarius A. But the central question remained haunting astronomers with its beautiful simplicity. What was it? What could possibly be powerful enough to orchestrate the grand celestial waltz of the entire Milky Way, yet remain so stubbornly, so completely invisible? The breakthrough we needed was not a bigger telescope, but a different kind of eye. An eye that could pierce through the dust, that could see in the wavelengths of light, utterly alien to our own senses. We turned to the infrared. From the high arid deserts of Chile and the dormant volcanic peaks of Hawaii, we built technological marvels, the Very Large Telescope, the Keck Observatory. These were not mere instruments. They were time machines and ghost detectors designed to capture the faint ancient heat of stars hidden behind the galactic veil. When those infrared eyes first opened, the view they delivered was not one of peaceful majesty. It was a vision of pure, unadulterated chaos, a maelstrom. Here in the central few light years of the galaxy, the stellar density is 1,000,000 times greater than in our quiet solar neighbourhood. You are looking at a metropolis of stars, a frantic gravitational swarm where suns jostle for position, like angry hornets in a hive. Massive blue-white giants burning through their fuel in a few short million years scream past one another at astonishing speeds. Their stellar winds, powerful enough to strip a lesser star of its atmosphere, collide in supersonic shockwaves that heat the surrounding gas to millions of degrees. Twisted filaments of magnetism, sculpted by the combined forces of this stellar pandemonium, thread through the entire region, glowing in the radio spectrum. It is a cosmic war zone, a place of both furious creation and breathtaking destruction, all orchestrated by a central unseen conductor. And it was within this bewildering frenzy that we had to find our ghost. We couldn't see the object itself, but we could see its work. We could watch its influence written in the motion of the stars caught in its grasp. The strategy was audacious, requiring a level of patience almost unheard of in modern science. Astronomers decided to chart the movements of the individual stars closest to the very centre, to track their positions with meticulous, painstaking precision, not for a day or a month, but for years, and then for decades. Each data point captured on a clear night was a single frame in a movie that would take a generation to film. They were treating these giant burning stars as tiny, weightless test particles, messengers sent back from the edge of an abyss. Their paths dictated by the pure, relentless laws of gravity would betray the nature of the beast they were forced to orbit. One star in particular became our primary witness. Known to science by the unassuming name of S2, it proved to be the ultimate celestial informant. While other stars followed wide, leisurely paths, S2 was on a kamikaze run. It swung through the galactic centre on a tight, perilously elongated orbit, a 16-year journey that brought it terrifyingly close to the invisible heart of the mystery. Year after year, the teams led by Reinhard Genzel in Germany and Andrea Ghez in California tracked its progress. They watched as S2, a star 15 times more massive than our own Sun, accelerated. It began to move faster and faster, still pulled inward by a gravitational force of unimaginable power. Alternative theories began to crumble. A dense cluster of old, faint stars. The combined gravity wouldn't be strong enough, and the cluster itself would have torn S2's orbit apart. A cloud of exotic dark matter particles. It wouldn't be compact enough to hold such a precise, stable orbit. Every new position logged for Watteau was another nail in the coffin for anything other than a single monumental object. Then came the moment of truth, the periastron passage. This is the point of closest approach, the moment the orbiting body feels the maximum pull of its master. In 2002 and again in 2018, astronomers around the world held their breath as S2 rounded the final turn. It was moving at over 25 million kilometers per hour, nearly 3% of the speed of light. It became a blur, a streak of light whipping around nothing. A gravitational slingshot of cosmic proportions flinging a colossal star around a point of absolute blackness. The arc of its turn was sharp, clean and perfect. It obeyed Kepler's laws of planetary motion with a mathematical purity that was both beautiful and terrifying. The case was closed. The dance of S2 had given us the answer. By measuring the exact shape and duration of its orbit, we could calculate the mass of the object it was circling. The number that emerged from the equations was staggering. 4.3 million. 4.3 million times the mass of our Sun, all of its gravitational might concentrated into a volume of space smaller than the orbit of Mercury. An object with that much mass crammed into such a tiny space, yet emitting no light of its own, could only be one thing. It was the verdict science had been chasing for 70 years. Our galaxy, our home, is anchored by a supermassive black hole. The ghost in the machine finally had a name, and its nature was more profound than we had ever imagined. But identifying our black hole was only the beginning of understanding it. Because when we compared Sagittarius A to its cousins in other galaxies, we discovered another profound mystery. Many galactic centres are violent, brilliant places. They are home to quasars, celestial blowtorches that shine with the light of 1 trillion suns, powered by supermassive black holes in the midst of epic feeding frenzies. These active galactic nuclei are the most luminous objects in the universe, visible from across billions of light years. They are cosmic monsters devouring entire stars and colossal clouds of gas, funneling the material into brilliant accretion disks that heat up to unimaginable temperatures before taking the final plunge. Our black hole does none of this. Sagittarius A is by cosmic standards a sleeping giant, a slumbering beast. Its energy output is shockingly pitifully low. If the most active black holes are raging infernos, ours is a barely smouldering ember. It is for all intents and purposes starving. The vast majority of the gas and dust swirling in the chaotic galactic centre is kept at a safe distance, either by its own orbital momentum or blown away by the fierce winds of the surrounding stars. Our monster is on a starvation diet, subsisting on nothing more than the occasional insignificant puff of interstellar gas or a tragically wayward asteroid. When it does manage to swallow one of these tiny morsels, we see the evidence. Faint fleeting flickers of X-rays and infrared light like sparks from a dying fire are emitted from the gas as it's heated and stretched on its final fatal journey. These flares are the only sign that the giant is not dead, merely dormant. A temporary eruption of energy, a brief sigh from the abyss before it returns to its deep and profound quiescence. This then is the stage upon which our story is set, a place of the most extreme contrasts imaginable. At the heart of the most violent, crowded and irradiated neighbourhood in the entire Milky Way sits a gravitational titan of impossible power, sleeping a quiet, nearly dreamless sleep. Its event horizon, the point of no return, is a mere 24 million kilometres across a cosmic pinprick on a galactic scale, yet its influence commands the fate of 400 billion stars. For millennia, this delicate paradoxical balance has held. The chaos of the galactic centre has raged on, but the sleeping monster at its heart has remained undisturbed, a quiet anchor in a sea of stellar violence. But in the cosmos, no state is permanent. Change is the only constant. And deep within that celestial swarm, something had begun to stir. Unseen for years, a small, unassuming condensation of gas, a lonely wisp in the maelstrom, was discovered to be on a most extraordinary path. It was not in a stable distant orbit like the star S2. It was not part of the random churn of the central cluster. This object, later named G2, was on a direct and unavoidable collision course. It was falling, accelerating relentlessly on a trajectory that would take it right through the fiery, chaotic accretion zone and into the immediate crushing gravitational domain of the sleeping giant. The feast was about to begin. The quiet heart of our galaxy was about to wake up, and for the first time in human history, we would have a front row seat. And so, after decades of patient listening, of staring into the silent, star-choked heart of our own galaxy, we had grown accustomed to the quiet. We had mapped the frantic orbits of the S-stars, those celestial loyalists pirouetting around an unseen sovereign, their dance the only definitive proof of the monster lurking in the dark. We had measured its mass 4 million times that of our Sun, and charted the boundaries of its gravitational kingdom. Yet for all its power, Sagittarius A was a sleeping giant, a dormant volcano. Its past tantrums were etched in the bubbles of high-energy gas extending thousands of light-years above and below the galactic plane, but its present was one of near-total quiescence. It seemed content to starve, subsisting on only the thinnest wisps of interstellar wind, a diet wholly insufficient for a creature of its stature. We watched, we waited, and we wondered if we would ever see it stir in our lifetime. Science, however, rarely unfolds according to a schedule. The greatest discoveries are often not found, but stumbled upon emerging as faint whispers from the background noise of the universe. The stage for this unexpected cosmic drama was set not in a bustling control room, but in the quiet, methodical analysis of data. It was 2011, and a team of astronomers led by Stefan Gillissen at the Max Planck Institute in Germany were engaged in the painstaking work of charting the galactic centre. Their instrument of choice was the Very Large Telescope, or VLT, perched high in the bone-dry air of Chile's Atacama Desert. Its 4 monumental mirrors, each a marvel of engineering, worked in concert, their combined vision piercing through the dense curtains of dust that veil the Milky Way's core from our eyes. For years they had been building a moving map of this chaotic region, tracking the stars as they swung through their orbits, a celestial ballet choreographed by the black hole's immense gravity. It was a project defined by patience, a slow-motion epic revealing itself frame by frame, year by year. They were looking for the familiar patterns, for the subtle shifts in stellar positions that would refine our understanding of the central engine. They were not looking for anything new. But the universe, it seems, had other plans. Deep within the overlapping images, hidden in the glare of neighbouring stars, a faint, unassuming smudge appeared. It was an anomaly, a ghostly wisp of infrared light where no known star was supposed to be. In the grand tapestry of the galactic centre, a region teeming with 1 million suns packed into a space just a few light-years across, it was almost nothing. A glitch in the detector, perhaps, a trick of the light. But it persisted. It was there in the 2010 data, fainter still in the archives from 2008, and even a hint of it in images from 2004. This was no phantom. It was real. And more importantly, it was moving. The team designated it G2, a dry technical name for what would soon become the most intensely scrutinized object in the galactic centre. When they plotted its position over time, a chilling and electrifying picture began to form. This was not a star on a stable repeating path. It was a traveller on a one-way journey. Its trajectory was not a gentle looping ellipse, but a terrifyingly elongated, almost suicidal plunge. It was falling, accelerating with every passing month, drawn inward by an inescapable force, and the target of its kamikaze dive was Sagittarius A itself. The initial disbelief within the astronomical community quickly gave way to a palpable once-in-a-generation excitement. The calculations were checked, rechecked, and confirmed by independent teams. The orbital path was undeniable. G2 was swinging in on a course that would bring it to its periastron, its point of closest approach, at a mere 200 astronomical units from the supermassive black hole. That's just a few times the distance from our Sun to Pluto. In cosmic terms, it was a razor's edge, a hair's breadth from the maw of the beast. The flyby was predicted to occur in the summer of 2014. For the first time, we had advance notice of an object about to be subjected to the full unmitigated fury of a supermassive black hole. It was as if the universe had sent us an invitation handing humanity a front-row ticket to a gladiatorial contest between gravity and matter. Every major observatory on the planet and in orbit above it began to retask their schedules. A global campaign of observation began a coordinated effort to turn the world's most powerful electronic eyes towards this single unfolding event. The sleeping giant was about to be prodded, and we would be there to see what happened when it woke up. But what exactly was G2? This question became the central puzzle, the answer to which would dictate the nature of the show we were about to witness. The initial observation suggested it was not a star. It was too diffuse, too stretched out. The light it emitted was the characteristic glow of ionized hydrogen gas heated to a few hundred degrees with a smattering of dust. The simplest and most compelling model was that G2 was exactly what it looked like, a simple, pristine cloud of gas, perhaps 3 times the mass of our planet Earth, a cosmic raindrop drifting through the galactic downtown. If this were true, its fate was sealed, and the scientific implications were staggering. We were about to witness in real time the fundamental process that has powered the universe since the first galaxies formed the feeding of a black hole. We were going to see it eat. The physics of this impending encounter were both elegant and brutal. A solid object like a star might be able to withstand the gravitational strain of such a close pass, its own self-gravity holding it together. But a fragile, tenuous cloud of gas possesses no such internal fortitude. For such a diffuse object, the most terrifying force is not gravity itself, but the gradient of gravity, what physicists call a tidal force. As G2 would plummet towards Sagittarius A, the edge of the cloud closer to the black hole would feel a significantly stronger gravitational pull than the trailing edge. This differential would act as a cosmic stretching rack. The black hole's gravity would not simply pull on the cloud, it would get its talons into it, mercilessly pulling it apart from the inside out. The process is famously known as spaghettification, a whimsical term for an unimaginably violent event. Theoretical models run on supercomputers across the globe all painted the same grisly picture. As G2 approached periastron, it would be stretched and deformed, its spherical shape distorted into a long, thin streamer of gas. It would cease to be a cloud and would become a river of matter unspooling like a ball of yarn caught on a celestial hook. This act of destruction, however, was only the prelude. The truly spectacular part, the scientific goldmine, was what would come next. The shredded remains of G2, no longer a coherent object but a smear of disorganized atoms, would not simply fly past the black hole. A significant portion of this gas, now captured by the black hole's gravity, would be unable to escape. It would be dragged into a new decaying orbit, forming a temporary miniature accretion disk, a swirling vortex of superheated matter spiraling towards the event horizon. This is the moment astronomers had been dreaming of. Sagittarius A is so quiet because it is starved of fuel. Its immediate environment is remarkably clean, swept clear of the abundant gas that fuels the brilliant quasars we see in the distant universe. We have theories about how accretion disks work, how they glow with furious energy, as friction and compression heat the infalling matter to millions of degrees. But these theories were based on observing black holes that are perpetually on billions of light-years away. G2 offered something unprecedented, the chance to see an accretion event from its very beginning, to watch the engine turn over and roar to life. The predictions were glorious. As the gas from G2 began its final fatal spiral, it would light up the darkness. The intense heat generated by the churning disk would unleash a torrent of radiation across the entire electromagnetic spectrum. We would see a flare-up in radio waves as electrons were whipped around by powerful magnetic fields. Most dramatically, we expected a brilliant flash of X-rays, the high-energy scream of matter, being heated to the brink of oblivion just before it crosses the event horizon and vanishes from our universe forever. This celestial fireworks show would be more than just a spectacle. It would be a unique physical experiment, a probe sent directly into the most extreme environment we know. The light from this flare would carry information about the physics of the accretion flow itself. How fast does the gas fall in? How turbulent is the disk? How efficiently is gravitational energy converted into radiation? These are some of the most fundamental questions in high-energy astrophysics, and the answers were seemingly about to be delivered to our telescopes. The death of G2 would be the birth of a new understanding. We could test our complex computer simulations against hard observational reality. We could finally get a glimpse into the mechanics of the cosmic engine that lies at the heart of our own home galaxy. The anticipation in the years leading up to 2014 was almost unbearable. Every new observation of G2 was scrutinized, every subtle change in its shape and brightness analyzed for clues. The cloud was indeed beginning to stretch its leading edge, accelerating away from its trailing tail, confirming the brutal effects of the black hole's tidal forces were already taking hold. It was behaving exactly as a simple gas cloud should. The model seemed to be correct. The stage was set for the most well-documented act of cosmic cannibalism in history. Teams of theorists refined their predictions, calculating the expected brightness of the coming flare, the timing of its peak, and the spectral signatures we should look for. Observers booked their time on telescopes months, even years in advance, not wanting to miss a single moment of the show. A sense of collective focus settled over the astronomical world, a shared purpose, uniting researchers across continents. They were all waiting, watching this tiny faint smudge of light as it made its final approach. They were watching a doomed messenger, a fragile ghost about to be offered up to the silent god at the centre of the galaxy. Its sacrifice promised to illuminate the darkness, to answer questions that had plagued us for decades, and to finally reveal the true nature of the slumbering monster next door. The clock was ticking down to the moment of impact, the moment the feast was set to begin. Everything we thought we knew about black hole accretion was about to be put to the ultimate test. The universe was about to perform for us, and all we had to do was watch. The year 2014 dawns not with a whisper, but with a silent collective breath held across an entire planet. For years, every calculation, every simulation, every career staked on the fate of an insignificant-looking cosmic traveller had pointed to this single inexorable window in time. The celestial stage was set. The lead actor, the unassuming gas cloud G2, was now making its final desperate plunge towards the gravitational guillotine at the heart of our galaxy. The audience, humanity itself, had assembled its finest eyes to watch the spectacle unfold. Across the globe, a planetary nervous system of steel and glass, silicon and ambition awakens and turns its gaze toward the constellation Sagittarius. In the bone-dry air of Chile's Atacama Desert, the 4 colossal mirrors of the Very Large Telescope, each wider than a city bus, pivot in unison. Their adaptive optic systems, shimmering marvels of engineering flex and warp, hundreds of times a second cancelling out the twinkle of Earth's atmosphere to achieve a vision so sharp it could spot a single flame on the surface of the moon. Their goal is not to see the black hole itself, for that is an impossible task, but to witness the death glow of its victim, to trace the ghostly infrared signature of G2 as it stretches into a luminous ribbon. Thousands of miles away atop the sacred peak of Mauna Kea in Hawaii, the twin Keck telescopes, their segmented eyes gleaming under a canopy of impossible stars, join the vigil. They are hunters searching for the unique spectral fingerprints of superheated hydrogen and helium, the elemental screams of a cloud being torn asunder. These terrestrial giants are not alone in their watch. High above in the silent airless realm of orbit, our space-based sentinels are also aimed at the galactic core. The Chandra X-ray Observatory, a 3-ton celestial predator, focuses its nested mirrors to detect the most violent energetic outbursts. The astronomers who command it are anticipating a cataclysm, a ferocious blast of X-rays generated as G2's gas is compressed and heated to millions of degrees just before its final fatal ingestion. This would be the definitive flare, the cosmic smoke signal proving that Sagittarius A was finally having its long-awaited meal. Circling alongside it are other sentinels like the European Space Agency's XMM Newton and NASA's New Star, each tuned to a different dialect of this high-energy language, ensuring that not a single photon of the predicted feast goes unrecorded. And below them all, scattered across continents, an army of radio telescopes listens intently from the Carl G. Jansky, Very Large Array, in New Mexico, its 27 dishes gliding across desert tracks to the Atacama, large millimeter, submillimeter, array in Chile, they are the ears of this global endeavour. They listen for the synchrotron radiation, the telltale radio hum of electrons spiralling in the immense magnetic fields girding the black hole's maw, a hum expected to rise to a deafening crescendo. Every one of these instruments, representing decades of ingenuity and billions of dollars in investment, is part of an unprecedented coordinated campaign. Data streams begin to pour into supercomputing centres from every corner of the Earth and from the vacuum of space itself. Algorithms honed by years of simulations stand ready to pass the flood of information, to find the pattern in the noise, to pinpoint the exact moment the cosmic fireworks would begin. In control rooms from Germany to California, the atmosphere is electric. Screens flicker with telemetry and nascent data plots. Coffee pots are drained and refilled. The hushed, focused energy is that of a mission control center. Moments before a rocket launch, except the event horizon they are watching, is 26,000 light-years away, and the countdown has been running for over a decade. The script as we understood it was brutally simple and profoundly elegant. G2, a simple cloud of primordial gas, would be no match for the most powerful gravitational object in the Milky Way. As it swung around the black hole in its tight elliptical orbit, it would cross a gravitational point of no return known as the Roche limit. Here the tidal forces, the difference in the pull of gravity on the near side of the cloud versus the far side, would become stronger than the cloud's own self-gravity. The stretching, which had been subtly observed for years, would become a violent runaway process. The cloud would be spaghettified, attenuated into a long thin stream of plasma, a cosmic noodle of incandescent gas. A portion of this stream would be flung away, ejected back into the galaxy on a new hyperbolic trajectory. But the rest, the doomed remainder, would be captured. It would spiral inwards, forming a temporary glowing accretion disk around Sagittarius A. This process, the conversion of gravitational potential energy into heat and light, was the source of the anticipated blast. It would be a celestial blowtorch briefly illuminating the black hole's immediate environment, giving us a rare and precious glimpse into the physics of accretion in a low-luminosity galactic nucleus. It was a perfect cosmic experiment handed to us by sheer chance. Weeks turn into months in early 2014. The tension mounts with every new observation. The infrared data from the VLT confirms it. G2 is getting closer. It's no longer a compact blob. It's visibly elongated, a teardrop of gas pointing accusingly toward the unseen monster. The front of the cloud is moving demonstrably faster than its tail, a clear sign that the tidal forces are at work just as the models predicted. Everything is proceeding according to the celestial schedule. The stretching is real. The orbital path is confirmed. The moment of pericenter, the point of closest approach, is calculated with astonishing precision. Late spring of 2014. At this point, G2 would be a mere 20 billion miles from the event horizon. While that sounds like a vast distance in gravitational terms, it is intimate. It is life-threateningly close, only a few hundred times the radius of the event horizon itself. It is well within the zone of tidal destruction. The global network of telescopes holds its collective gaze. The data streams become a torrent, and then the moment arrives. G2 rounds the pericenter mark. It whips around the gravitational anchor of Sagittarius A at a staggering 5 million miles per hour, a blistering 1% of the speed of light, and begins its long climb back out of the gravity well. The control rooms fall silent. All eyes are on the data flowing from the X-ray observatories, the primary heralds of the expected feast. Seconds stretch into minutes, minutes into hours. The plots on the screens remain stubbornly, unnervingly flat. There is no sudden spike in X-ray emissions. There is no brilliant flare heralding the consumption of shredded gas. The heart of our galaxy, the place where a supermassive monster was supposed to be tearing its victim apart in a blaze of glory, remains shrouded in its customary eerie quiet. A faint flicker is detected, a minor brightening in the X-ray spectrum, but it is a pale shadow of the predicted inferno. It is the equivalent of a single match striking in a dark stadium where you were expecting a hydrogen bomb to detonate. It is statistically significant, yes, but scientifically bewildering. It is nothing. Astronomers check their instruments. Could there be a malfunction in Chandra's XMM Newton's detector saturated by an unforeseen solar event? But the signals from every orbiting observatory tell the same impossible story. The radio arrays listen to the sound of silence. The expected crescendo of synchrotron radiation never comes. The hum of the galaxy's core does not change its tune. It is as if the main act of the opera never took the stage, as if the guest of honor never arrived at the banquet. The infrared telescopes in Chile and Hawaii provide the most perplexing clue of all. They watch as the gas cloud, though undeniably stretched and distorted from its perilous journey, largely survives its encounter. It emerges from its close shave with oblivion not as a shredded ribbon of plasma being devoured, but as a still coherent, albeit elongated, object. It continues along its orbit, pulling away from Sagittarius A, wounded but intact. The show was over, and nothing had happened. A profound seismic shock begins to ripple through the astronomical community. This wasn't a minor discrepancy. It wasn't a case of the fireworks being a little dimmer than expected. This was a fundamental categorical failure of prediction. The cosmic script which we had written with the seemingly infallible ink of gravitational physics was wrong. The universe had refused to follow our narrative. The silence from the galactic center was not an absence of data. It was the data. It was a roaring, definitive statement that our assumptions about this encounter were deeply and fundamentally flawed. This non-event became one of the most important astronomical results of the decade precisely because it was a failure. It forced a painful and exhilarating re-evaluation of everything we thought we knew. If G2 was not a simple gas cloud, then what was it? How could something withstand the titanic tidal forces so close to a supermassive black hole? What hidden structure, what unseen core could have provided the gravitational glue to hold it together against all odds? And what did this mean for Sagittarius A? Our theories of black hole accretion, the very models we use to understand how these monsters grow and influence their host galaxies, had been built on the assumption that they would readily consume any gas that strayed too close. But here was our own black hole presented with a meal on a silver platter, and it had for all intents and purposes refused to eat. Did it have a more complex environment than we imagined, a sort of gravitational shield that protected it? Was the process of accretion far less efficient, far more mysterious than our elegant equations had led us to believe? The quiet at the heart of the Milky Way had suddenly become the loudest mystery in modern astrophysics. The failure to see the expected fireworks didn't close a chapter of exploration. It blew the book wide open. Every scientist who had watched, waited and predicted was sent back to the drawing board, armed not with the triumph of confirmation, but with the far more powerful catalyst of profound surprise. We had journeyed 26,000 light years, armed with our most advanced technology and our deepest theories to witness a feast. Instead, we were confronted with a riddle, a cosmic puzzle box that challenged the very core of our understanding. The question was no longer what would happen to G2. The urgent, all-consuming question now was, what is G2? The moment of closest approach arrived not with a bang, but with a profound, echoing silence. Across the globe, in the hushed control rooms of our greatest observatories, a collective breath was held, waiting for the celestial fireworks that had been promised for years. We had aimed the planet's most powerful eyes, the Very Large Telescope in Chile, the Keck Observatory in Hawaii, our sentinels in space at the heart of our galaxy, anticipating a spectacle of cosmic violence. We were poised to witness the final agonizing moments of the gas cloud G2, to see it shredded by the tidal forces of Sagittarius A, and consumed in a blaze of high-energy radiation. This was meant to be our ringside seat to a black hole feast, a once-in-a-generation opportunity to watch the mechanics of accretion unfold in real time. The models were clear, the physics seemingly undeniable. A diffuse cloud of hydrogen and helium, stretched thin by its long fall, would be torn asunder by the black hole's gravitational gradient, its constituent atoms superheated into a brilliant screaming plasma as they spiraled into the abyss. We expected a flash, a flare in the X-ray and radio spectrum that would outshine everything in the galactic core, a definitive signal that the banquet had begun. But the flash never came. The hours ticked by, turning into days, then weeks. The data streams pouring in from around the world all told the same disquieting story: nothing. The region around Sagittarius A remained stubbornly, frustratingly quiescent. There was no grand eruption, no surge of energy, no death cry from a disintegrating cloud. The monster at the heart of the Milky Way, presented with what we believed was a perfectly prepared meal, appeared to have simply refused to eat. In the scientific community, the initial anticipation curdled into a palpable confusion, a deep and unsettling bewilderment that rippled through astronomy departments and international conferences. We had made a bold public prediction based on decades of established theory, and the universe had quietly, calmly proven us wrong. The great cosmic drama had ended before the first act was complete, leaving us with an empty stage and a script that suddenly made no sense. It was a humbling, deeply perplexing anticlimax, a cosmic ghosting that forced us to confront a stark reality. Either our understanding of G2 was fundamentally flawed, or our grasp on the physics governing the most extreme environment in our galaxy was far more tenuous than we had ever dared to admit. The silence from the galactic centre was not an absence of information. It was a resounding declaration, a new and profound mystery that demanded we abandon our assumptions and begin the investigation anew, sifting through the phantom echoes of an event that never was. The immediate aftermath was not a period of abandonment, but one of intensified scrutiny. The lack of a cataclysmic feast became in itself the most compelling data point. This was no longer a mission to observe a predictable event. It had transformed into a celestial autopsy, a forensic investigation into a non-disappearance. Teams of astronomers, instead of archiving their data, redoubled their efforts, initiating the most extensive and prolonged monitoring campaign ever focused on a single object near Sagittarius A. The game had changed. The question was no longer, how will it die? But why did it live? Every photon captured by our telescopes in the months following G2's pericenter passage became a crucial piece of evidence in this new cosmic puzzle. The European Southern Observatory's Very Large Telescope, using its powerful Symphony instrument, continued to track G2 with relentless precision, peering through the dense veils of dust and stars that shroud the galactic core. Its infrared eyes were uniquely suited to this task, capable of detecting the faint warm glow of hydrogen gas even in this bewildering environment. Simultaneously, radio telescopes like the Very Large Array in New Mexico listened intently, straining to hear the faintest whispers of interaction, the subtle radio chatter that might betray the true nature of this enigmatic object. What emerged from this persistent, painstaking observation was a picture far stranger and more compelling than the simple destruction we had anticipated. The data compiled and cross-referenced from multiple instruments across the electromagnetic spectrum began to paint a portrait of a survivor. G2 had not escaped its encounter unscathed. Far from it. The gravitational tidal forces had exacted a punishing toll. As it whipped around the black hole at a staggering 10 million kilometers per hour, it was subjected to an unimaginable strain. We watched mesmerized as the data revealed the object being stretched into a spectacular, impossibly elongated filament, a process astronomers call spaghettification. The front of G2, being closer to the black hole, was pulled forward with immensely greater force than its trailing edge. It was like a cosmic tug-of-war played out on a galactic scale, with gravity itself as the rope. The object was drawn out its once compact form, distorted into a luminous streamer of gas and dust many times its original length. It resembled a single delicate brushstroke of light painted across the darkness, a testament to the brutal gravitational artistry of a supermassive black hole. The models had predicted this stretching, this tidal deformation. It was the one part of the forecast that the universe had honoured. But it was what lay within this stretched-out filament that completely overturned our expectations and plunged the scientific community into a state of profound reassessment. Deep inside that distorted shroud of gas the core of G2 had endured. Against all odds, it remained a coherent, gravitationally bound entity. While its outer layers had been stripped away and smeared across its orbit like a celestial contrail, the heart of the object had held together. It had weathered the storm. A simple homogeneous cloud of primordial gas, the kind we had modelled, would have had no chance. It possesses no central anchor, no dense core to resist the black hole's relentless shearing forces. Such a cloud should have been completely unzipped, its atoms scattered into the accretion disk, its identity erased forever. The survival of G2's core was a direct, unambiguous contradiction of the pure gas cloud hypothesis. It was the smoking gun that told us we were not looking at what we thought we were looking at. This tiny, resilient kernel of matter, steadfast in the face of gravitational annihilation, had invalidated years of theoretical work and transformed our understanding of the event. It was not a failed prediction, it was a revelation, a signpost pointing toward a much deeper, more complex truth about the strange objects that wander the perilous landscape of our galactic centre. This single stubborn fact, the survival of a core, sent shockwaves through the world of astrophysics. It was as if we had predicted a fragile glass sculpture would shatter upon impact with a hammer, only to watch it dent slightly and bounce away. The very foundation of our G2 models had crumbled because they were all built upon the assumption that it was in essence a simple structureless puff of gas and dust. The physics of tidal disruption for such an object is well understood and unforgiving. A body is torn apart when the difference in gravitational pull across its diameter becomes greater than the object's own self-gravity, the force holding it together. For a diffuse cloud with negligible self-gravity, this threshold is crossed far from the black hole. Its destruction should have been swift, total, and inevitable. The mathematics was unequivocal. Yet the observational evidence from our post-Pericenter campaign was equally unequivocal. G2 had a robust gravitational anchor, something dense and massive enough to withstand the immense tidal forces at its closest approach. The clean, elegant model of a simple gas cloud being tidally disrupted and accreted had been a beautiful theory, but the universe had presented a messy, contradictory, and infinitely more fascinating reality. The immediate consequence was an eruption of intense scientific debate, a period of inspired chaos where old certainties were discarded, and new, often radical ideas were thrust into the spotlight. Conference halls that were once filled with confident presentations on the expected X-ray light curves from G2's demise now hosted impassioned arguments and blackboard-filling equations as theorists scrambled to explain the inexplicable. The community fractured into competing camps, each championing a different explanation for G2's baffling resilience. Could G2 be a planetary nebula, the shed outer layers of a dying star which would be puffier than a normal gas cloud but still might not explain the core's survival? Or was it something far more exotic, a novel type of celestial object unique to the bizarre ecosystem of the galactic centre? Every new dataset from the VLT or Keck was seized upon, scrutinized and interpreted in different ways, fueling the controversy. This wasn't a quiet academic disagreement. It was a fundamental clash of paradigms played out in preprint archives and scientific journals. The sheer strangeness of the observation had thrown open the doors of possibility. Without the anchor of a confirmed theory, scientists were forced to think creatively to push the boundaries of what we considered possible in such an extreme environment. One of the most compelling and rapidly ascendant new theories proposed that G2 was not a gas cloud at all, but something far more substantial hiding in plain sight. Perhaps this new line of reasoning meant we were witnessing a star swaddled in a thick opaque cocoon of gas and dust. In this model, the object we had been tracking for a decade was not the cloud itself, but a star producing the cloud. This star, likely a young hot star still enshrouded in its natal envelope, or an older dying star shedding its outer layers, would provide the crucial gravitational anchor that the pure gas cloud model lacked. Its own powerful gravity would be sufficient to hold its immediate atmosphere together, even as the black hole's tidal forces stripped away the more tenuous extended parts of its dusty shroud. This star in a cocoon hypothesis elegantly explained the central paradox. It accounted for the observed stretching of a gaseous component, while simultaneously explaining the survival of a dense, compact core. It suggested we hadn't been watching a doomed cloud at all, but rather a star getting a cosmic haircut, a close shave by the razor edge of space-time near Sagittarius A. It was a dramatic and compelling pivot, reframing G2 from a passive victim into a resilient protagonist in its own gravitational drama. This paradigm shift did more than just offer a potential solution to the G2 puzzle. It forced us to critically reassess the entire environment surrounding our galaxy's central black hole. If an object like a dust-enshrouded star could be masquerading as a gas cloud, what else were we misinterpreting in this chaotic, visually obscured region? Our models of the accretion flow onto Sagittarius A had been built on the assumption that we could accurately identify the types of material falling inward. G2 was meant to be the perfect test case, a clean, simple meal. Its unexpected nature suggested that the menu was far more complex and exotic than we had imagined. Perhaps the galactic centre is littered with these strange shrouded stars born in the turbulent stellar nurseries that orbit the black hole. If so, their interactions with Sagittarius A would be fundamentally different from those of pure gas clouds. Instead of providing a steady, easily digested stream of fuel, they might offer only fleeting partial snacks, their dusty outer layers stripped away, while their stellar cores continue on their orbits largely intact. This would profoundly alter our calculations of how and how often Sagittarius A actually feeds. The black hole might not be a picky eater, but rather its potential meals are far more robust and self-protective than we ever knew. The mystery deepened further as we turned our attention from G2 itself to the medium through which it was travelling. Our inability to predict its fate highlighted our ignorance not just of the object, but of the space it inhabited. The immediate vicinity of a supermassive black hole is not empty. It is filled with a complex, tenuous medium of hot gas, powerful magnetic fields, and the fierce stellar winds from thousands of massive stars locked in orbit. Did this environment play a role in G2's survival? Some scientists propose that G2 was not just a star in a cocoon, but that it was experiencing a phenomenon known as a bow shock. As the star and its dusty envelope ploughed through the hot ambient gas surrounding the black hole at supersonic speeds, it would create a shockwave in front of it, much like the one created by a supersonic jet. This bow shock would compress the gas and dust around the star, effectively reinforcing its cocoon and making it even more resilient to the black hole's tidal forces. In this scenario, the surrounding environment wasn't just a passive backdrop. It was an active participant in the drama, providing a protective shield that helped G2 weather the gravitational storm. The mystery was no longer confined to a single object, but had expanded to encompass the intricate invisible dance of plasma winds and magnetic fields that choreographs the life and death of everything in the galactic nucleus. And so, we found ourselves standing at the edge of a new frontier of ignorance. We had journeyed to the heart of the Milky Way, expecting to witness a predictable act of consumption, a simple story of predator and prey. We had hoped to confirm our elegant theories to watch the universe behave as our equations told us it should. Instead, we were handed a profound and beautiful puzzle, a nested doll of mysteries, each one revealing another deeper question within. The anticlimactic passage of G2 was not a failure of observation, but a triumph of discovery. It was a perfect example of the scientific process at its most thrilling, a moment where nature refuses to conform to our expectations, forcing us to dismantle our old ideas and build something new, something truer in their place. The lack of a feast told us more than a spectacular explosion ever could. It pointed to a richer, more complex reality at the galactic centre, a place populated by strange, resilient objects, and governed by an intricate interplay of forces we're only just beginning to comprehend. The question was no longer simply what happens when a gas cloud meets a black hole. The question, now infinitely more compelling, had become what else is lurking in the shadows, at the heart of our galaxy, and what other secrets are waiting to be revealed. And so the great celestial fireworks show we had all gathered to witness never happened. The cosmic banquet anticipated for years across the globe ended without a single course being served. A profound silence emanated from the galactic core, an anticlimax so deep it was almost a roar in itself. Where titanic flares should have erupted, there was only the familiar unsettling quiet of Sagittarius A. The cloud G2 had rounded the point of its closest approach, its perilous periapsis passage, and had simply kept going, stretched, battered and glowing with the heat of its ordeal, yes, but fundamentally intact. It had stared into the abyss, and the abyss, it seemed, had barely taken notice. For the astronomers who had staked their reputations, their telescope time, and their intricate models on a spectacular collision, this was more than a mere disappointment. It was a deep fundamental puzzle. The laws of physics, as we understood them, were not supposed to be suggestions. They were ironclad. A diffuse unsupported cloud of hydrogen gas with a mass of perhaps 3 Earths should have been unravelled by the black hole's tidal forces like a fragile thread of smoke in a hurricane. Those forces, a manifestation of gravity's brutal geometry, should have stretched the cloud's leading edge while its trailing edge lagged behind a process known as spaghettification. This grotesque elongation would have torn G2 into tenuous streamers of plasma, which would then have spiraled onto the black hole's accretion disk, compressing and heating to millions of degrees. The result would have been an outburst of X-rays and radio waves, a luminous death cry echoing across 26,000 light-years. But the cry never came. G2 had defied its own eulogy. It was a moment of profound cognitive dissonance for the entire field of astrophysics. The models weren't just slightly off. They had predicted an entirely different reality. This wasn't a failure of observation. The data on G2's trajectory were exquisite, refined over a decade of meticulous tracking. The failure, it seemed, was in our very premise. We had misidentified the victim. The question that echoed through observatory control rooms and university colloquia was no longer when G2 would be consumed, but what precisely was G2 in the first place? The universe had presented us not with a spectacle, but with a far more valuable prize, a genuine mystery. And in science, a mystery is an invitation, a doorway into a deeper level of understanding. The initial letdown quickly sublimated into a fierce, galvanized curiosity. The scientific community, a global network of minds connected by a shared passion for the cosmos, began to rally. The data archives were thrown open, supercomputer simulations were recalibrated, and a storm of new ideas began to swirl. Out of this intellectual tempest, a new consensus began to slowly, painstakingly crystallize. It was an idea that was both elegant in its simplicity and profound in its implications. Perhaps we'd been looking at G2 all wrong. We saw a cloud, a simple, pristine condensation of interstellar gas destined for oblivion. But what if the cloud was not the protagonist of this story? What if it was merely a costume? A dusty, gaseous shroud concealing something much more robust at its heart. The theory that gained traction, the one that began to satisfyingly explain G2's impossible resilience, was the star within a cloud model. This hypothesis proposed that G2 was not a free-floating gas cloud at all, but rather a young, dusty star enveloped in a thick cocoon of its own natal material. It wasn't a ghost. It was a ghost with a skeleton. Suddenly the pieces of the puzzle began to slot into place with an audible click. A star, even a relatively modest one, possesses its own powerful gravitational field. It acts as a cosmic anchor, a central point of cohesion. As G2 embarked on its terrifying plunge towards Sagittarius A, this hidden star became the cloud's salvation. The black hole's tidal forces were still immense, still working to pull the gaseous envelope apart. But they were now competing against a second force, the star's own gravity desperately clinging to its surrounding atmosphere. The gas was no longer an unsupported wisp. It was gravitationally bound to a dense, compact object. This stellar heart provided a gravitational backbone, a shield that held the cloud together against the worst of the shearing forces. The black hole could stretch and distort the envelope, peeling away its outer layers, but it couldn't simply dissipate the core structure. The star was the ship's hull, navigating the storm while the gas was merely its tattered sails. This wasn't just speculation. The evidence was there, buried in the decade of data we had already collected. Astronomers began a forensic re-examination of G2's light spectrum and its orbital mechanics. A free-floating gas cloud subject to the slightest gravitational perturbations and drag from the surrounding medium would likely follow a messy, slightly chaotic path. But G2's orbit was surprisingly clean almost perfectly, Keplerian, tracing a precise and predictable ellipse, the kind of orbit you would expect from a solid point-like mass. Furthermore, as it approached the black hole, its shape, while dramatically elongated, never completely broke apart. It maintained a distinct condensed head, a bright knot of infrared emission that stubbornly refused to disperse. This was the telltale signature of a solid object ploughing through the galactic center's environment. When infrared observatories looked closer at this bright knot, they detected signs of a warm, dusty surface heated not just by the proximity to the black hole, but from within. It was the unmistakable glow of a shrouded stellar engine. The star within a cloud model painted a dramatic new picture. Imagine a young, newly formed star swaddled in the remnants of the molecular cloud from which it was born. These types of stars are common in the turbulent nurseries of the galaxy, but this one had been born with a terrible destiny. Through some gravitational interaction, perhaps a close encounter with another star or a binary system, it was flung out of its stellar creche and placed on a high-speed, highly elliptical trajectory aimed directly at the supermassive black hole. For its entire journey it wore its origins like a cloak, a vast envelope of dust and gas that made it appear as something it was not. When we first discovered it, our telescopes saw only this enormous cool shroud, and mistook the entire object for a simple cloud. We were so captivated by the costume that we failed to recognize the actor wearing it. The G2 event then was not the story of a black hole's meal, but the story of a stellar survivor. It was a cosmic close shave, a testament to the power of a star's own gravity to protect it even in the most hostile environment in the entire Milky Way. But solving the mystery of G2's identity was only half of the revelation. Its survival also forced us to look at its would-be predator Sagittarius A in a completely new light. The black hole's failure to produce a feast wasn't just because G2 was a more resilient target. It was also because the black hole itself exists in a state far more complex than we had imagined. Our supermassive black hole is not sitting in an empty void, patiently waiting for a meal to be delivered. Instead, it is immersed in a vast, searingly hot and incredibly diffuse atmosphere of its own making. This is the hot accretion flow, a nearly invisible sea of plasma 10 million degrees, Kelvin swirling in a slow eternal vortex around the event horizon. This plasma is the captured stellar wind from the dozens of massive young stars orbiting the galactic center, a constant supply of superheated gas that the black hole steadily sips upon. This boiling ethereal ocean has profound consequences for anything attempting to approach Sagittarius A's. It isn't a vacuum, it's a medium, a cosmic headwind. As G2, the star, and its cloud plunged through this hot accretion flow at millions of miles per hour, it experienced a phenomenon known as ram pressure. It's the same force you feel when you stick your hand out of a moving car window, but on an astronomical scale. This pressure acted like a celestial blowtorch, stripping away the outermost, most weakly bound layers of G2's gaseous envelope. The gas didn't fall neatly toward the black hole. It was ablated, scraped off, and mixed into the already turbulent, superheated plasma of the surrounding flow. This process actually heated the cloud, causing it to glow brightly in the infrared, and giving us the illusion of an impending feast, but it also robbed the black hole of an easy meal. The environment of Sagittarius A had effectively pre-processed the offering, dispersing much of it before it could ever reach the inner accretion disk. This led to the final crucial piece of the puzzle, a refined understanding of our black hole's eating habits. Sagittarius A is what we call a quiescent or dormant black hole. For its immense mass of 4 million suns, it is stunningly faint, radiating less energy than our own sun. For decades we wondered why. Was it simply starved of fuel? The G2 event provided a definitive answer. No, it's not starving, it's just an extraordinarily inefficient engine. It is constantly fed by the stellar winds that create the hot accretion flow, but the physics of that flow make it incredibly difficult for matter to actually lose its angular momentum and fall across the event horizon. The plasma is so hot and diffuse that its particles are more likely to be flung back out or orbit indefinitely than to be consumed. Our black hole is a simmering giant, not a gluttonous monster. It subsists on a slow, steady trickle from this vast reservoir, a diet so inefficient that a morsel like the gas from G2 was little more than a single drop in a boiling ocean. It was not enough to trigger a significant outburst. The system simply absorbed the minor disturbance without any visible indigestion. The climax of the G2 saga, therefore, was not one of light and fury, but of quiet, profound insight. We had come expecting to witness a simple act of cosmic consumption, a straightforward story of predator and prey. We had set up our cameras for a spectacle of brute force, a demonstration of gravity's ultimate power. Instead, the universe handed us a lesson in subtlety and complexity. We learned that the galactic centre is not a simple void punctuated by a singularity, but a dynamic, intricate ecosystem. It is a place where stars can be wrapped in dusty cocoons, where they can survive harrowing journeys past the point of no return, shielded by their own gravity. And it is a place where a supermassive black hole, the most powerful engine of destruction we know, can reign in a state of surprising tranquility, its appetite moderated by the very atmosphere it creates. The feast we had anticipated was never for the black hole, it was for us. It was a feast of data, a banquet of new knowledge that forced us to discard old assumptions and embrace a more nuanced, more elegant model of the cosmos. G2's survival was not a failure of prediction, but the successful discovery of our own ignorance. It provided us with a new celestial laboratory, a unique probe that had journeyed through the previously unseen environment around our galaxy's central engine and emerged to tell the tale. And as the dust settled both literally and figuratively, astronomers realized that G2 was not the end of the story. Its journey had given us a new lens. Looking back at the galactic centre through this new filter of understanding, we began to see hints of other similar objects, a family of G-objects on equally daring orbits, each one a potential new mystery, a new messenger from the edge of the abyss promising to reveal even more secrets about the life and habits of the sleeping giant at the heart of our Milky Way. And so, the cosmic moment we had all been waiting for arrived. The world's greatest observatories, our most sophisticated eyes on the universe, were all trained on a single infinitesimal point of darkness at the heart of our own galaxy. Years of calculations, countless hours of debate, and the collective anticipation of a global scientific community had led to this precipice. We were poised to witness a celestial banquet, a violent, spectacular feast, as Sagittarius A consumed the unsuspecting gas cloud G2. We expected a blaze of glory, a final brilliant scream of light and energy as matter crossed the event horizon. We braced for the fireworks, but the universe in its infinite and often ironic wisdom had a different lesson in store for us. The crescendo never came. The great celestial roar we had tuned in to hear was replaced by a profound and revealing silence. Where we anticipated a supernova of activity, there was only the faintest cosmic whisper, a subtle stirring in the dark. The feast, the dramatic galaxy-altering spectacle we had all imagined simply didn't happen. It would have been easy to label this a failure, a cosmic anticlimax, a prediction gone wrong. Yet what we experienced was something far more valuable, more transformative than any explosion could ever have been. We had asked the universe a simple question, expecting a simple, violent answer. Instead, it responded with a complex and elegant truth, a revelation that has reshaped our entire understanding of the monstrous hearts of galaxies. The story of G2 is not one of a failed fireworks show. It is the story of how a silent passage taught us more than the loudest cataclysm ever could. The first and most stunning lesson came from G2 itself. For this object to survive its perilous journey, it had to be far more than the simple diaphanous cloud of gas and dust we had initially believed it to be. As it approached its point of closest passage, the periapsis had entered a gravitational crucible of unimaginable intensity. The tidal forces exerted by Sagittarius A are not a uniform pull. They are a differential force of pure destruction. The side of G2 closer to the black hole was being pulled with exponentially greater force than the side farther away, a relentless gravitational stretching, designed to tear any loose collection of matter into a thin spaghettified stream. We watched, expecting this process to unfold with textbook brutality, anticipating the moment the cloud would be unravelled like a ball of cosmic yarn, its contents drained into the maw of the black hole. But G2 held on. It stretched, yes, elongating into a tormented, distended shape more than 160 billion kilometres long. It was distorted beyond recognition, a testament to the sheer gravitational power it was enduring. Yet its core integrity remained. It refused to dissipate. This was not the behavior of a simple gas cloud. A cloud is a passive, fragile thing easily dispersed by the slightest cosmic wind, let alone the gravitational grip of 4 million suns. G2's resilience was a direct challenge to our assumptions. It told us in no uncertain terms that something dense, something gravitationally bound, must lie hidden within its gaseous shroud. The most compelling hypothesis that emerged from this stunning survival was that G2 is not a cloud at all, but a star, or more likely a binary star system, two stars locked in a close orbit that had merged together, cloaking themselves in a vast extended atmosphere of shed material. Imagine two stars dancing together for millions of years. In the chaos of their merger, they puff out a huge bloated envelope of gas, creating the very object we mistook for a simple cloud. Deep inside that envelope, however, lies the hard, dense kernel of the merged star itself, a gravitational anchor holding the entire structure together. This anchor is what gave G2 the strength to withstand the tidal forces of Sagittarius A. The black hole could stretch and warp its outer layers, pulling at its gaseous cloak, but it could not break the central stellar heart of the object. This discovery was revolutionary. It meant that stars, perhaps of a very specific and unusual kind, could not only exist, but could also navigate these most treacherous of cosmic pathways, skimming the very edge of oblivion and living to tell the tale. We had been looking for a victim, a sacrifice to the black hole. Instead, we found a survivor, a testament to the unexpected tenacity of objects in the most extreme environments the universe has to offer. G2's survival wasn't a disappointment. It was our first clue that the galactic centre was populated by far stranger and more resilient creatures than we had ever dared to imagine. The second profound revelation delivered by G2's silent passage concerned not the object itself, but the very space through which it travelled. For decades we have modelled the immediate environment around Sagittarius A based on theory and distant observations. We pictured a near vacuum, a region of space swept clean by the black hole's immense gravity, with only a thin, hot, tenuous accretion disk of swirling matter. But G2 in its journey acted as a cosmic probe, a celestial canary sent deep into the mineshaft of the galactic centre. As it moved, it didn't just interact with the black hole's gravity, it interacted with the medium that fills the space around it. And by carefully analysing the light from G2, as it was stretched and distorted, we began to build a new and far more complex picture of this enigmatic region. As G2's leading edge plunged toward the black hole, it began to encounter a kind of cosmic headwind. We observed it slowing down, but not just from gravitational effects. It was experiencing drag of friction caused by pushing through a medium that was significantly denser than anyone had predicted. This was not the pristine vacuum of our models. This was a complex dynamic atmosphere, a thin but pervasive fog of hot gas and plasma, swirling in a complex dance dictated by both gravity and powerful magnetic fields. G2's journey was like dragging a net through an unseen ocean. By studying what the net caught and how it was buffeted by the currents, we could finally map the sea itself. The friction experienced by the cloud generated a faint bow shock ahead of it, a subtle ripple in the fabric of the galactic centre's environment. This shock wave, though invisible to the naked eye, could be detected in specific wavelengths of light, providing us with unprecedented real-time data on the density, temperature and velocity of the ambient gas. Furthermore, the shape of G2's elongated tail provided clues about the magnetic fields that permeate this space. These fields, we now understand, are not neat and orderly. They're a tangled, chaotic web that channels the flow of ionized gas, creating currents and eddies that influence everything in their vicinity. G2's tail didn't just trail passively behind it. It was sculpted by these invisible magnetic lines, twisting and turning in ways that directly mirrored the structure of the field. We were for the first time getting a weather report from the heart of the Milky Way. We were learning about the cosmic winds that blow the magnetic pressures that squeeze in the ambient density of the air just a few light months from a supermassive black hole's event horizon. This was information we could never have gleaned from a distance. G2 had to physically travel through this region to feel its effects, to experience its subtle pressures, in order to transmit this invaluable knowledge back to us across 26,000 light-years. The great non-event had transformed into an unparalleled atmospheric survey, turning our galactic core from a theoretical abstraction into a tangible living environment with its own unique and turbulent climate. And what of the monster itself? What did G2's journey teach us about the feeding habits of Sagittarius A? The predicted flare-up, the burst of X-rays and radio waves from the black hole's final consumption, never materialized. But this absence of drama was in itself a profoundly important piece of the puzzle. It told us that our supermassive black hole is an exceptionally fussy and inefficient eater. Even as G2's outer layers were stretched and some of its gas was undoubtedly siphoned off, this material did not simply plummet straight into the event horizon. The process of accretion we were learning is not a simple drain. It is a complex, chaotic, and remarkably inefficient process. Instead of a feast, we may have witnessed a light snack, or perhaps just the playing with of food. Faint subtle flickers in X-ray and infrared emissions were detected in the months and years following G2's closest approach. These were not the brilliant death cries we had anticipated, but rather the energetic equivalent of cosmic crumbs falling from the table. They suggested that small parcels of gas stripped from G2 were slowly making their way inward, joining the swirling chaos of the accretion flow. But most of the material, it seems, either remained bound to G2's stellar core, or was flung past the black hole into a new, wide orbit destined to return perhaps centuries or millennia from now. This observation provides a crucial calibration point for our models of black hole growth. Supermassive black holes like Sagittarius A don't necessarily grow through singular cataclysmic feeding events. Their growth over cosmic time might be dominated by this slow, steady, and inefficient simmering, a continuous trickle of matter rather than a series of dramatic floods. Our black hole is not a voracious, ravenous predator, but a sleeping giant subsisting on a near-starvation diet. The material in its vicinity is held in a delicate balance. The black hole's gravity pulls it inward, but the energy and angular momentum of that same material conspire to keep it in orbit, resisting the final plunge. It takes a significant disturbance to upset this balance and initiate a major feeding event. G2, despite its dramatic trajectory, was simply not enough of a disturbance to awaken the beast. It was a fly buzzing past a lion, and in learning this we learn something fundamental about the state of our own galaxy. The Milky Way is in a period of relative quiescence. Its central engine is idling, not roaring. This quietude stands in stark contrast to the violent quasars we see in the distant early universe galaxies, whose central black holes are consuming entire stars a day shining with the light of 1 trillion suns. The story of G2 helps us understand the transition from that violent youth to the comparatively peaceful middle age our galaxy now enjoys. The silence from Sagittarius A was not an absence of data. It was the most important data point of all, a direct measurement of the profound calm that lies at the heart of our galactic home. Perhaps the most exciting legacy of this entire episode is the discovery that G2 is not alone. Once we knew what to look for an object that behaves like a star but looks like a gas cloud, we began to find others. Astronomers scouring archival data and initiating new surveys identified a new class of celestial objects, which they aptly named G-objects. We now know of G1, G3, G4, G5, and G6, each on its own unique and highly elliptical orbit around Sagittarius A. This transforms the narrative entirely. G2 was no longer a cosmic anomaly. It was the founding member of a previously unknown family, a new species in the galactic zoo. These G-objects appear to be a common feature of the galactic center, a population of strange, dust-enshrouded stars, born from the violent dynamics of binary star systems in this crowded and chaotic region. They are time capsules, each one a product of the extreme gravitational environment near the black hole. Studying their orbits, their composition, and their origins will give us a new window into the history of star formation at the galactic core. Each one is a future experiment, a probe waiting to be launched. We can now track an entire swarm of these objects, each on a trajectory that will bring it close to Sagittarius A at some point in the future. We are no longer waiting for a single once-in-a-lifetime event. We now have a recurring natural laboratory that will allow us to test the laws of physics in the realm of extreme gravity again and again. G2 was the pioneer, the one that first blazed the trail and showed us the way. Its siblings will now follow, and with each close passage we will add another chapter to our understanding, refining our measurements and deepening our insights into the intricate dance of matter and gravity around our galaxy's central engine. The story of the Great Black Hole Feast did not end with a silent passage. It ended with the discovery of a whole new frontier, and so we stand at the threshold of a new era of exploration. The journey of G2 has already pushed our best instruments, the Keck Observatory, the Very Large Telescope, to their absolute limits. But a new generation of sentinels is now turning its gaze toward the heavens. Telescopes like the James Webb Space Telescope, with its unparalleled infrared sensitivity, can pierce through the dense curtains of dust that have long hidden the galactic centre from our view. On the ground, behemoths like the extremely large telescope and the 30-metre telescope are under construction. With mirrors tens of meters across, they will provide us with images so sharp, so clear, that they will be able to resolve the G-objects not just as points of light but as extended structures. We will be able to watch in breathtaking detail as they are stretched and contorted by the black hole's gravity. We may even be able to directly image the stellar cores hidden within their dusty veils. These next-generation observatories will move us from inference to direct observation. We will no longer have to guess at the nature of the galactic centre's environment. We will map its magnetic fields and track its turbulent winds in real time. We will chart the orbits of stars and G-objects with such exquisite precision that we will be able to test Einstein's theory of general relativity in ways that have never before been possible, searching for the faintest deviations that might hint at a new, more complete theory of gravity. The mystery that began with a single peculiar cloud has blossomed into one of the richest and most promising fields of astrophysical research. The universe, it seems, rarely gives us the answers we expect. We look to the heart of our galaxy, anticipating a story of destruction, a simple and violent tale of consumption. Instead, we found a subtle and far more profound narrative of survival, of resilience, and of the complex interconnected life of the galactic core. G2 was not the feast we had prepared for, but it became our Rosetta Stone, allowing us to decipher the secrets of an environment we had only ever glimpsed through a veil of theory. It reminded us that in science the most exciting discoveries often come not from confirming what we think we know, but from the breathtaking surprise of being proven wrong. The story of Sagittarius A is far from over. Its greatest secrets remain locked away, waiting for us to ask the right questions to build the right tools. And as we continue to gaze into that deep and silent darkness, we do so with a newfound wisdom, knowing that the most important lessons are often not shouted in a blaze of light but whispered in the quiet heart of the cosmic night.